Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on the basicity and nucleophilicity. This is mostly on amines, basicity and nucleophilicity of amines. I'll be just going through I'll be going through the level of basicity of amines, how they act as both basic and nucleophiles, so how they act as bases and nucleophiles, and explaining why certain amines are more nucleophilic than other amines. And you have to know this for your exam, because they'll give you an example of two questions where they'll give you an example in the question where they give you two diagrams of two compounds, and I want you to explain why one compound is more basic than the other, and also be able to understand what it means to actually be basic. So yeah, I'm gonna go through that today. So amines display both basic and nucleophilic behavior, and we'll look at quaternary ammonium salts as well. So basicity. So amines contain a lone pair of electrons, and this makes the amine attracted to a positive charge and in particular protons, and this gives them basic properties of being able to accept a proton, as shown below. Now, when I mean this has two examples here. So they contain a lone pair of electrons. This makes amines attracted to a positive charge. So being able to donate a lone pair, is what we would describe as being a Lewis base. So this is, I'm showing you both. I'm just pretty much showing you here that it's a base. Remember, there's two types of bases: Bronsted-Lowry bases and there's Lewis bases. When it comes to lone pairs, electrons, a Lewis base is just a base that donates a lone pair of electrons. A Bronsted-Lowry base is a base that accepts protons, and it just does both of those properties here. It gives them the basic property of being able to accept protons. So amines contain a lone pair of electrons. This makes the amine attracted to a positive charge, and they're able to donate that lone pair of electrons. So it's clearly acting as a Lewis base here, and it gives them the basic property of being able to accept a proton, as shown below here. It's acting as a Bronsted-Lowry base, and so you can see the lone pair on the nitrogen is always on the nitrogen. That's the part that actually acts. That's actually causing the reaction, or that's where the valence electrons are, right? And in this case, the lone pair of electrons are on the nitrogen here. We don't describe the carbon. The carbon already has as many bonds as it can already. It hasn't got any more lone pair of electrons. So I only say this because in the exam they really want you to emphasize the fact that it's on the nitrogen. It's really like they really want you to say that it's on the nitrogen. And if you don't say it's the lone pair's on the nitrogen, I've seen examples where they won't give you the mark at all because you haven't mentioned that the lone pair is on the nitrogen. So don't just say the lone pair on the amine, because yes, it's technically on the amine, but you have to specifically say the lone pair on the nitrogen of the amine. Alright, so now I'm going to continue on. So nucleophilicity. A lone pair on the nitrogen also makes amines nucleophilic, so it's attracted to a positive charge. They react with halogen alkanes, acyl chlorides, and acid anhydrides in nucleophilic reactions. So, I mean, this lone pair here, it makes it basic. It also makes it nucleophilic. So the lone pair of nitrogen makes it nucleophilic, and it can react with, it's attracted to a positive charge, i.e. it's attracted to electrophiles, and it can react with halogen alkanes and in multiple different mechanisms: nucleophilic addition, nucleophilic substitution, nucleophilic addition and elimination, all the type of nucleophilic reactions that you're aware of. The amines are able to do that because they're nucleophilic. Now, we have quaternary ammonium salts. So quaternary ammonium salts can be used as cationic surfactants, and surfactants lower the surface tension of a liquid, which means that they can act as detergents, wetting agents, emulsifiers, foaming agents, and dispersants. The cationic surfactant has a hydrophilic head, which is able to interact with water, and a hydrophilic tail, which interacts with organic matter such as oils or fats, which makes it amphipathic. So there's a lot to unpack there. I'm just going to go through that again because I don't want to just skip past things. So the quaternary ammonium salts can be used as, first of all, quaternary ammonium salts, right? They're not really described as being well, first we have to think what a quaternary ammonium salt is. They're considered not being basic, or definitely not acting as nucleophiles. I don't know about the basic. I'm pretty sure they're not acting as base as well, because remember what we said here. We said because of the lone pair, because they contain a lone pair of electrons, this makes the amines attracted to a positive charge, in particular a proton, and this gives them the basic property, right? But remember what the structure of what the structure is of a quaternary ammonium salt, right? There's no lone pair here. There's no lone pair. In fact it's even got a dative covalent bond. It's used all of its electrons. So now it can't act as it can't donate a lone pair of electrons, and it can't really accept a proton really. So it can't. We don't generally consider quaternary ammonium salts as being basic, but they can do certain. I mean, maybe if it's acting as if it's in a salt form, maybe if it's the bromine or the chloride, maybe those can, because they have lone pairs. If it gets separate bromide ion, that's fine. But in itself, ammonium no, or ammonium compounds no. Now the second thing that I talked about here was that the fact that they can act as cationic surfactants. So surfactants, what they do is they lower the surface tension of a liquid. But what does that actually mean? Well, what does that actually like? Because I remember my teacher said this to me, and I just pretended like I knew, but I think I asked him after school, after the lesson, what does that actually mean? And I don't remember it particularly to mind right here, but I've got an example from the brightonscience.com, and he said that what it is just that adding a surfactant to a coating or detergent, it lowers the surface tension of the liquid, so it means that it will flow more easily, and it covers the entirety of the surface. So usually when you think about a drop of water, you think about it in a drop, because because if you know biology, right? I mean, I don't want to dwell into to biology too much here, but the reason why water is a droplet, or if you get like a bottle of water and you accidentally spill like a little tiny droplet onto the table, right? It doesn't, the water isn't flat on the surface. It's like a little, it still looks like a little bubble, and that's because there's tension between between the bonds in the hydrogen. Sorry, there's tension between water molecules, as in because there's hydrogen bonding, that causes tension, and it kind of pulls it into shape. The very electronegative oxygen atom and a very positive charged hydrogen atom. Sorry, that should not be there. Right there. Remember when we talk about hydrogen bonding, partially negative oxygen atom, partially positive hydrogen atom. Well, oxygen is very electronegative, but in that, remember the delta negative part, delta positive, and that's very, very strong hydrogen bonding there. And actually what happens is that between different water molecules, you also get that tension, because there's going to be hydrogen bonding between those molecules there. But when you have a quaternary ammonium salts, it breaks that tension. You can't reform those bonds, and now you've broken that tension, and now it means that water is not going to be in that kind of droplet form, and it can run much more easily. And that's useful when you're talking about acting as a detergent, wetting agents, emulsifiers, foaming agents. You need to at least know one of them. But in terms of one of them, the one I always remember about these is a cationic surfactant, or you can usually just get away with surfactant. But just in case, detergents, wetting agents, emulsifiers, foaming agents, dispersants. Remembering at least one of those, it would be quite useful for you. Now, the cationic surfactant itself has a hydrophilic head. And if you remember, I don't want to dwell too much into biology, but if you know about biology and phospholipid bilayers, they have both a hydrophilic head and a hydrophobic tail. Now, obviously, this isn't a phospholipid bilayer, no, but salts work like certain soaps. If we're talking about soaps, right, or wetting agents or anything like that, like soaps kind of work in a very similar way to that as well. Though they'll have a hydrophobic head that will bind to certain dirt or oils, and then the hydrophilic part is bonding to the water. So after it's bonded to the oil or the dirt or whatever it is, the hydrophobic part will bind to the dirt or the oil, whatever it is, and then the hydrophilic part, because it's all bonded to it's all in the same molecule. I'm trying to get an example here. So imagine this is the hydrophobic head, and it's the hydrophilic tail, right? say this bit of dirt here, this hydrophobic part will bind to the hydrophobic part, right? And then because this part is hydrophilic and it's all on the same molecule, it will, as the water passes through it, it'll bind to water because it's hydrophilic, and it'll pull the dirt with it, and then it'll go down the drain. So that's kind of like in case you go very confused why that's useful. That's the main reason why. I usually talk about when we're coming to soaps, but quaternary ammonium salts, I do believe you can use them with soap as well, or with the one that usually comes to mind is shampoo, but double check that one just in case. But I'm pretty certain quaternary ammonium salts are you can use them with hair conditioner. But that's why I was just explaining why it was important to have a hydrophobic part here and how it interacts with oil and a hydrophilic part. So hydrophobic here, hydrophilic. But when you have a compound that's when you have a compound that has both a hydrophobic and a hydrophilic end on the same molecule, we call that amphipathic. That's what it means. So if it's both hydrophobic and hydrophilic, it's called amphipathic. Now, what we covered so far, so properties of amines, right? So let's just sum up what we've done so far. So properties of amines. So we're talking about the basicity. Right, so we talked about the basicity. And it's lone pairs accept electrons. So lone pairs accept protons, not electrons. Lone pairs are electrons anyway. So lone pairs accept protons. And to the nucleophility, we have to talk about the nucleophilicity. Lone pair is where the lone pair is actually attracted to a positive charge, which is the protons. But in doing so, it is basic. The reason why it's basic is also subject to also the reason why it's also nucleophilic. You know, the reason when you're explaining about the reasoning about being basic, it can also be applied to the reasons why it's nucleophilic. So lone pair is attracted to a positive charge. Strength of basicity. So, alright, so now we've gone through why it's basic and why it's nucleophilic. But now we're gonna have to now we got through the reasons, but then you have to understand now when you're in the previous video I talked about primary, secondary, tertiary, that's the classification of amines. Now that you know what if you haven't seen that video, go watch that video. I'll leave a link in the description to that video. But the reason why that's so important to know that is that the classification of amines, because different amines have a different ability in terms of basicity. So there's different orders of basicity. So certain amines or certain classes of amines are more basic than other classes of amines, and there's reasons for that. So and it all revolves around what being basic is, right? And I'll kind of and I'm gonna go through that really here. So strength of basicity, right? So we can evaluate the strength of amines basicity by considering its R groups. So strength of basicity, right? Strength of basicity, the basic strength of an amine depends on the availability of electrons. If the molecule's electron pair is more available, it will be a stronger base. Now this part here is so important because hopefully that whole thing highlights there. That is the basis of most of the questions when it comes down, not most questions, all questions when we're talking about bases and amines or how basic it is. That is what you need to understand about bases, is that the ability we're talking about the purpose of we're mostly talking about Lewis bases, right? We're talking here mostly about Lewis bases, that the ability of a lone pair to be donated. Remember, a Lewis base is a compound that is able to donate a lone pair of electrons here. Now, the more available the more available or the more accessible it is for that lone pair to be donated, or I mean you can talk about it acting as a Bronsted-Lowry base as well, a proton acceptor. So you can use either. In fact, I kind of use both in a way. I'll explain why I use both in a way. But the more available a lone pair is, the easier it will be for protonation, i.e. the easier it will be to act as a base. So the basic strength of amine depends on the availability of a lone pair of electrons for protonation. So if a lone pair is more available for protonation, so if you make there's certain ways to make the lone pair more available for protonation. I'm gonna go through that here. So this availability is often affected by the R groups. So the R groups can either push electron density or they can pull electron density. We use ammonia as a reference and evaluate whether specific R groups will increase or decrease electron availability in comparison to ammonia. So if it pushes electron density, right, which is, I'll go through what that actually is called. It has actually a specific name. Certain groups will push electron density. When they push electron density, it makes towards the nitrogen. If they push electron density towards nitrogen, it makes the lone pair on the nitrogen more available for protonation. If the R group pulls electron density away from nitrogen, it makes the lone pair less available for protonation and hence a weaker base. Okay, so I kind of, hopefully I made a lot of sense there. Yeah, I'm gonna go continue on. So when we talk about aliphatic amines, right? So alkylated amines are more basic than ammonia. So we usually use, I'm going to use ammonia here as the reference, because ammonia ammonia is a base, but there are compounds that are more basic than ammonia, and compounds that are less basic than ammonia. And I'm just kind of using ammonia as the standard, right? Well, Seneca did, because I said I use Seneca's videos to Seneca's lessons to make these videos, but alkylated amines are more basic than ammonia, because an alkyl group will actually, the alkyl R group will increase basicity, and that's because an alkyl R group pushes electron density towards the nitrogen, and this increases the electron density on nitrogen, making the lone pair more available for protonation, and this is called a positive inductive effect. Now, in certain examples, you don't have to actually say, I always say it, but in certain examples, saying this, sorry. Saying this is enough, because you can just the positive inductive effect is just the R group pushing electron density towards nitrogen to make the lone pair on the nitrogen more available for protonation. That's what really it means, really. But I always say it because sometimes I prefer, sometimes in the marketing they don't want you just to say positive inductive effect. They usually allow either or, but just to make sure you don't listen. This is probably like a 3-mark question, or 4, or how many. If they're asking you for a comparison, it might be 5 marks or whatever. But you would definitely complete this question in less than the time it takes. So if it's a 3-mark question, you can complete this question in 1 minute or 2 minutes instead of 3 minutes, or 1.5 minutes instead of 3 minutes. So I would just personally say that the R group initiates a positive inductive effect, which pushes electron density towards the nitrogen, making the lone pair of nitrogen more available for protonation. And that is undeniably, if that's all they want you to talk about, if that's just one point they want you to get across, you've 100% got all the marks there. If they want you to make a comparison saying this compound is this has a much stronger positive inductive effect, and you explain the reason why, because this is more alkylated, so and so. Okay, fine. I'll go through that at the end. This is in the only thing. Is it the? Yeah, cool. So okay, cool. So it didn't go through every example here, but I'll just say it after here. But all I'm trying to say is that making sure to say that I just don't just say positive inductive, even though it means really the same thing. You're not going to lose any time from saying it, but being able to understand the question, what they're asking, remember to always highlight what's the type of questions they say. Evaluate, then you have to evaluate, make sure to give both arguments and then give a conclusion. They're saying compare, make sure to actually make a comparison. Always make sure to answer the question. But if we're talking about the point of the question, or like the general understanding of what it means to be, which one is more basic, it always falls down to which one has the strongest positive inductive effect, which pushes electron density towards nitrogen the most, and which and if it pushes electron density to nitrogen the most, it makes the lone pair more available for protonation, and therefore it acts as a stronger base. And that's all it is. So what happens here, you can see, so this is an alkyl compound. The longer this compound, the longer this alkyl group, the stronger the positive inductive effect, and this pushes electron density towards nitrogen, which makes the lone pair more available for protonation. I don't know how many times I've said that right now. I'm just gonna keep saying it because that is the main point. I don't know, until you get sick of me saying it, I guess. And that's what we go there. But it's not just that. Secondary amines and tertiary amines are more. Let me just make sure that's No, it doesn't say that. I thought maybe I forgot to say that. But basicity increases with the type of amine. So because a secondary amine is more basic than a primary amine, because you have, right, if I did it like here, right, I'm gonna just take away this. I'm gonna take away this one of these H's here, right? The more R groups you have bonded to the hydrogen, really you're talking about, if you're talking about aliphatic R groups, right? If you're talking about aliphatic R groups, you have more, it's more alkylated. It said alkylated amines are more basic, and we said the reason why, because it increased because it pushes electron density. So the more R groups you have that's bonded to the nitrogen, the more available this lone pair is to protonation. I'll actually change this to make it more like this. Right? Now if I was to go even further and do this, right? We have another R group which is further pushing electron density towards we have another aliphatic R group that's making this compound even more alkylated, which is even further pushing electron density towards nitrogen, which is a stronger positive inductive effect, pushing electron density towards nitrogen again, making it more available for protonation, right? That's a terrible one. That's a terrible one. Sorry. Sorry about that in there, but the idea is, right, the more alkylated it is, the stronger the positive inductive effect. And that's what you need to know, right? That's not what you need to know. That is the basis of what I'm trying to say. So the more aliphatic alkylated groups. So the more alkylated it is, the more alkyl groups that's bonded to nitrogen, i.e. the higher the type of amine that's aliphatic. I'm getting my sources up here because I really want. There's two types of amines: aromatic and aliphatic, right? And R groups could be aliphatic or aliphatic or aromatic. And aromatic is a completely different reason. I'll explain why. But the more alkylated it is, the more aliphatic R groups, or the higher the type of class of amine that's aliphatic, the stronger the positive inductive effect, the more there's a real emphasis of a more electron density. The electron density being electron density is more strongly pushed towards the nitrogen, and therefore the lone pair is more available for protonation. Hopefully I said that enough times now that people can get my point. So we can say that aliphatic amine basicity strength is of order. You'd think that we usually think that the tertiary amine is more basic than the secondary amine, and the secondary amine is more basic than the primary amine. However, and there is a however to this, right? This is true. Well, it's not completely true, but theoretically, this is true because it's more available. However, due to the size of tertiary amines, they become less soluble and the general consensus of base is that they should be soluble in a solvent to form a solution. And in order to act, if in order for something to act as a base, it needs to be soluble in solution. However, tertiary amines are so large that they're just not soluble in solution, and therefore it can't technically act as a base, right? So even though it has the most available lone pair, because of this flaw, technically secondary amines and primary amines are considered to be more basic than tertiary amines, for that reason. So in reality, right, we'd actually go for this. It'd actually be secondary amines are the most basic, and the reason I say this because you will get any question in the exam where they may not directly say explain which is the most basic in terms of secondary amines, primary amines, and tertiary amines, but they'll give you an example, right? They'll give you, say, like these three compounds here, right? Sorry. They'll call this maybe compound, say compound Q, compound W, compound X, right? And they'll say which compound is the most likely to act as the strongest base, and you have to explain the reason why. So for your first mark isn't for, you don't have to your first mark in the mark scheme, they'll have something like this, but they don't want you to do it like this. They want you to actually physically say that the secondary amine, the first mark isn't actually a physical point of view saying this in one sentence. It's overall in a sentence. You've got the consensus in your answer that's saying that overall the secondary amine would be, if they gave you 3 examples and the one it was primary, secondary, and tertiary, the secondary amine is the most basic because it's soluble and it has the strongest positive inductive. I mean, it's soluble and has a strong positive inductive effect, which means that the alkyl groups would push electron density towards the nitrogen, making the lone pair more available for protonation, making it a stronger base. And then primary amine, this is a weaker base because it's less alkylated than the secondary amine. Though it's soluble, it'll be less basic because it has a weaker positive inductive effect, and it's because electron density is less. Electron density is pushed less towards nitrogen, and therefore the lone pair on the nitrogen is less available for protonation compared to a secondary amine. And then going for the third point, or if it's the tertiary amine, now usually they give you 2. Usually they just give you 2, but I just have to say this between the 2. But if they were talking about the tertiary amine, say that they usually like using the primary and the secondary. They usually like using those 2, or they use like an aromatic one. But if we're talking about the tertiary one here, just saying that though a tertiary amine is the most alkylated and usually has the strongest positive inductive effect, pushing and it's the most alkylated, pushing electron density the strongest towards nitrogen, making the lone pair of nitrogen more available for protonation. It's not soluble, and therefore, for it to act as a base, it must be soluble in solution to go and actually act as a base for in order for its lone pair to be protonated in solution. But it can't do that because of its size, and so because of its size, it's not soluble and can't form a solution. So that's the main thing you'll be talking about between those 3 here. So it's secondary, primary, tertiary in that order. Now, I said before the reason why I'll go for a reason why aromatic is very unsoluble. I put ammonia. Actually, ammonia probably is ammonia is a primary, so yeah, ammonia is really there really. So I'll have to go through that one there. But I'll go through why aromatic is less basic compared to the primary, secondary, and tertiary amines. But just quickly, the reason why a quaternary amine isn't is the least basic, and I said before, because there's no lone pair available for protonation. We've used all our lone pairs, so there's no lone pair available for protonation, and it's considered to be the least basic out of all of the amines. And yeah, so now I promise that we're coming up to the end of the video now. I'll try and not speak too much. I just really wanted to get through my point as to hammer home my point about bases. If you want to just skip to the part of the video where you feel like you need help with, just do that. But I'm nearly done now. So aromatic amines, right? So this applies to not just the one example that everyone uses, which is benzene, but it applies to all the aromatic groups. So all cyclo groups really it's the same principle. And aromatic amines are less basic than ammonia. And an aromatic R group will decrease basicity. And that's because an aromatic R group actually pulls electron density away from the nitrogen. And this decreases the electron density on the nitrogen, making the lone pair less available for protonation. Now we call that withdrawal effect or a negative inductive effect. Either or is fine. Benzene would have the strongest withdrawal effect though, due to the delocalized pi system. And I'm going to go into detail about what the withdrawal effect is, but just to make it clear here, the lone pair, the electron density is being pulled away from the nitrogen. Like I said before, if you're pulling electron density away from nitrogen, you're making that lone pair less available for protonation, and therefore it's a weaker base. That is the quintessential part of what I'm trying to say here. As to I can go through the complex reasons as well, but that is the main point that you need to hammer home in case you don't really get anything else. So that's the main point you need to hammer home. Your pull is a withdrawing, or hence the word withdraw, or negative is the opposite of the inductive effect. It's pulling away electron density away from nitrogen, making lone pair less available for protonation. Now with the withdrawal effect, right? So arenes, which is just a really technical name for types of benzenes, are electron withdrawing groups as they delocalize the electrons on the lone pair on the nitrogen and kind of emulsify it into the benzene ring. So if you have the lone pair here, right? This lone pair is kind of, so usually the lone pair will be like this here. I always draw my lone pairs as a electron. Actually, no, let me make this a bit bigger so I can yeah, go on. Now I can just do. I can pull this down here. Right, cool. So, right, I always draw my well, that's just not what I want to do. I always draw my lone pairs as an electron cloud because that is really and truly uh that is how electrons are really, or lone pairs are. They're in electron clouds. If you don't know what an electron cloud is, it's just an electron cloud is where there's a 95% probability where you will find electrons. That is it. So because electrons are randomly in this cloud here, they're randomly in this cloud, but there's a 95% probability that you'll find electrons in this cloud. You don't need to really know that definition. You have to know that definition by heart. It's just something that you can, I guess, know. I mentioned it in a previous video, but that's not the point. That's not the point. That's not the point of what this is. I was just kind of rambling on about a random point there. But when I was talking about the withdrawal effect here, right, I said they're withdrawing groups that they delocalize the electrons on the lone pair on a nitrogen and emulsify it into the kind of emulsify. I'll say it one more time. The withdrawing groups as they delocalize the electrons on the lone pair on the nitrogen. So this here, and they kind of like emulsify into the benzene ring, and this makes the benzene electron withdrawing and makes the nitrogen lone pair less available for protonation and hence less basic. That's just in maths that just means therefore. So if it's less likely for the lone pair, takes longer for the lone pair on nitrogen to accept a proton. Now what I mean here is, right, so when I always say that, I gave you the example of that lone pair kind of getting bigger or more available when I was talking about the positive inductive effect. I mean, maybe the cloud getting bigger isn't the best example of me showing it, but I was trying to make it very clear that the lone pair was getting more available for protonation when I was talking about the positive inductive effect. Now, when I was talking about the negative inductive effect here, when I was talking about a weaker positive inductive effect, I was talking about getting kind of like smaller. That's not what's happening, but I was trying to emphasize that it's getting less available for protonation. But when we're talking about the negative inductive effect, this kind of electron cloud here is getting actually pulled towards the aromatic group, right? It's kind of, so it's like more like this here. That's a terrible cloud, right? That's also a terrible cloud, but the idea that it's less available for protonation because it's more closer towards the aromatic group, because it's so electron withdrawing, as a very strong negative inductive effect or withdrawal effect, and it really makes this lone pair less available for protonation because it's closer towards here. It's actually it's not available. It's in reality it's so not available. That's the best way I can say it. It's very unavailable for for a proton to come here and protonate, be protonated. So it's very difficult for this lone pair to be protonated because it's not really available. What I mean by availability is like, I mean, it's how easy it is to actually protonate it. And I was trying to say here is less likely for the lone pair, or it takes longer for the lone pair of nitrogen to accept a proton. Now with benzene, benzene is so electron withdrawing because that delocalized pi system that I kind of talked about before. Should I leave the link in the description to the structure of benzene? Yes, I'll leave the two links in the description. It's so electron withdrawing that it's almost kind of like this, like to the point where it's actually nearly kind of pulling it so much into the ring. And so that's like, this is ultimate form of just being not available for protonation. And therefore it's less likely to be protonated, and therefore it's the weakest base. Well, it's not the weakest base. The quaternary ones are the most, because they have no lone pair available left. But that's why they're considered to be even less basic than tertiary amines. And yeah, hopefully this video was helpful, and that's it. Also, I've got to say.